Okay, so now that we introduced that there are multiple test error rates in the multiple testing scenario, and we also established the family-wise error rate, we now want to discuss how we can design a test such that the family-wise error rate is controlled. And the reason why we discuss this is because the random field theory approach that is implemented in the software packages FSL and SPM that controls the family-wise error rate using a maximum statistic. So when we will talk about random field theory, the first question that we will ask is what is the probability for the maximum of a random field to exceed a certain value. So we will discuss the probability distribution of the maximum of a random field, and the reason why we do this is because if we know that, then we can create a test that exerts maximum statistic-based family-wise error rate control. So that's now the topic. So, and this is this maximum statistic is used for both voxel level inference and cluster level inference in fMRI. So what people really like to report is the cluster level family-wise error corrected p-value, and this relates to the maximum of the clusters that you observed. And again, the idea is that you use the maximum of some statistics of interest to control the family-wise error rate. Of course, then the family-wise error rate for clusters is over the number of clusters and not over the number of voxels. That I think most people don't really appreciate, but that's how it is. So in any case, so the motivation for discussing maximum statistic-based FWER control, FWER control, should be somewhat clear, because it's the target of the random field theory approach. And also, if you look at another thing is, if you really are not interested in random field, but you want to do permutation testing, then also in permutation testing, multiple testing control of the family-wise error rate always works with the maximum statistics. So in this case, you would try to simulate the null distribution and approximate the distribution of the maximum statistic there. So regardless of random field theory or sampling approaches, the maximum statistic-based family-wise error rate control is a central thing in multiple testing control. Good. Having said that, again, we first should talk about what the family-wise error rate is. So informally, it's the family-wise error rate is the probability for one or more type 1 errors over the family of hypotheses. And the idea of family-wise error rate control in a test is now, of course, to keep this, by the testing procedure, to keep this probability smaller or equal to some significance level, for example, 0.05. Yeah? So what this means then, if you find or if you control the family-wise error rate at a level of 0.05, that means that the probability to observe one type 1 error over the family of hypothesis is smaller than 0.05, but also, for example, the probability to observe 20 type 1 errors, if you have 100 tests, for example, is smaller than 0.05. In fact, the probability of observing 1 or 2 or 3 or 4 and so on type 1 errors is smaller than 0.05. Now, first, we need to somehow state, to understand how the maximum statistic plays into that, we have to state this probability a bit more formal, so that it's easier to write than what I just wrote. So we now define the family-wise error rate. So not the significance level, but the error rate, like the size of a test, so the alpha of a test, as the probability over or under the assumption that let's say over the set of true null hypotheses. I will write up what this notation means in a second. That one or more tests come out 1. So there are these intersection and union. Sorry, there are these intersection and union statements, and they will come up all the time. So it's important that you know what this should exactly mean. So this here, so this intersection, this should mean null hypothesis holds at all I in I0. So that's what this statement here says. So you look at the probability for this event. So this is an event, of course, which we will discuss in a second. Under the assumption that the null hypothesis holds at all I in I0. Now you can, of course, have multiple things. So either I0 equals I, so that would be the complete null hypothesis scenario. So then you would look at the probability for this event of one or more false positives under the assumption that the null hypothesis is true for all tests, so for example all locations in the brain, or you can have the scenario that I0 is just a subset of I, so then you only worry about the probability where the null hypothesis actually holds, because if the null hypothesis doesn't hold somewhere, then of course you don't get a type 1 error there. So it doesn't make sense to talk about the probability of a type 1 error if the null hypothesis at this location doesn't hold at all. Yeah. So the important thing is that this probability, so this alpha family-wise error, is the probability under the assumption that the null hypothesis holds for at all locations or for all hypothesis I0. So in comparison to the single test scenario, of course in the single test scenario, this is just the assumption that the null hypothesis holds. Here it's the assumption that the null hypothesis holds for all hypotheses which are in this index set I0, which either be all hypotheses or a subset. Of course, if I0 is empty, so if the alternative hypothesis holds everywhere, then of course there is no family-wise error rate, because it's never an error if you reject the null hypothesis, yeah, because the alternative hypothesis is always true. So so we assume that I0 is can either be the whole index set of hypotheses, a subset, but it's not going to be empty. Because it's empty, then there is no family-wise error rate. So that's one thing. The other thing is this thing here, and that's actually more interesting. So here we have a union statement over, again, our I in the I0 set. So these are, of course, again, all the indices where the null hypothesis holds. And now we have the event phi y equals 1. So this is, of course, the test outcome that rejects the null hypothesis. And the question is now how to interpret this union statement. And the important thing here is that this is an AND OR statement. So in principle, so if one writes this out a little bit, in principle this means phi y equals 1 and or phi 2, or we should rather say, because this is a little bit too easy, I1, I2, where these I1, I2, IN0 are elements in this null hypothesis set I0. Now the question is how to read this. And this union statement you should always read as AND OR. Here also AND OR, and here AND OR. So verbally this means you're talking about the event that the test at the first true null hypothesis comes out 1, and or at the second true null hypothesis comes out 1, and or at the third, and so on, and or at the last of the true null hypothesis indices. And the important thing is that you can have AND OR for all of these union statements, meaning that you can either have the case, for example, that you can read all of them as ANDs. So at the first location the test comes out 1, and at the second it comes out 1, and so on. So this would refer to the event that you have type 1 errors for all of the true null hypotheses. You can have any mixture of AND OR, and you can have only OR statements. So if you only read this with OR statements, then you're talking about the event that the test comes out 1 at the first true null hypothesis, or at the second, or at the third, or at the fourth, and so on. And that means that if it's this OR reading, that it comes out at least at 1. So it must be at 1, so either at the first or the second or the third. So that's the case that there's actually only one type 1 error. Then you can have any numbers of and or readings, or you have type 1 errors at all of the locations, so you have M0 type 1 errors. Yeah? So this is how to interpret these statements here, so this intersection statement and this union statement. So a little bit more to get used to is this union statement that is just a logical union, which is an AND/OR union. So it's so like if you write A is in A cup B, so if A is in A and B, that means that if you do Venn diagrams, you like Venn diagrams, this can be that either A is in, so if this is big A, this is big B, that A is in A, or that A is in B, or that A is in A and B. Yeah? So this is then how to read these union statement. And this is here important because it goes with the interpretation of one or more type 1 errors. Yeah, so this is the same thing here as N0, as what we've seen above, that N01 is larger or equal to 1. Yeah, questions about this, because this is quite crucial. Good, that seems to be roughly clear. Now, this is just again the definition of the error rate. It's not about controlling it yet, and it's not about significance level. This is just the error rate, like the size of a test, which is the probability for type 1 error. Here we're talking about the probability of one or more type 1 errors over the set of hypotheses. And now we want to control it using a significance level. So we now establish the family-wise significance level. Alpha prime, and a test then, a test is said to be of family-wise significance level alpha prime if its family-wise error rate is equal to or smaller than the family-wise significance level alpha prime. Yeah. So yeah, and now the question is, so this is so this would be a test. So if the family significance level alpha prime is for example 0.05, then this test is set to control the family-wise error rate at the level alpha prime FWE. So say something else, and that's the family-wise significance level control at level. Yeah. So a test controls the family-wise error rate at a significance level of alpha prime family-wise error rate if its family-wise error rate is smaller or equal to alpha prime. And again, you can have here the scenario of an exact test, meaning that the significance level corresponds to or is equal to the family-wise error rate, or you can have a conservative test that the family-wise error rate is smaller than the significance level, and you can have a test that is not of significance level alpha prime and would be a liberal test if the family-wise error rate is larger than this. So a test controls the family-wise error rate at the significance level alpha prime if this inequality holds. Good. And with all this in place, we can now actually show that the maximum test statistic can be used to control the family-wise error rate at some significance level alpha prime. Yeah, so first we need then to define what we mean by the maximum test statistic. And to this end, we call that, we assume that all of these tests that we are looking at have their individual test statistics, gamma E. Yeah. So again, you can think of doing a t-test at each voxel, and then for each voxel you have a t-statistic. And you know that for each voxel, the t-statistic is distributed according to a t-distribution. Now we are interested in the maximum test statistic, which we write as this. So of course it depends on the data. So it's a function of the data, and it corresponds to the maximum over all null hypotheses. So this is what this small 0 here should mean. It's the maximum over all the tests where the null hypothesis holds of the individual test statistics. So if we have, for example, if we have a realization, so let's say we have a GLM at each location, so that's our GLM for I to m voxels, and we did a contrast vector, let's say beta, whatever, we did a contrast vector so that we test bi1 equals 0, so we use the contrast vector that has a 1 at the first entry and 0s everywhere else. From estimating the beta parameters and the variance parameter, then we can construct a list of t statistics, so a statistical parametric map of all the t statistics, which then, for example, I mean, you see them all the time because these are these where you see the blobs, but that, for example, looks like this. We have 4.1, 7.1, 8.2, 6.1, 5.9, 4.1. So this would be now a vector comprising all our t statistics. So this would be gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6. And let's assume that the null hypothesis actually holds at all of those. So then the maximum over all these here, our gamma I, y, in this realization would be 8.2. Yeah? So that's the maximum of the test statistics. And you should now, so if you think if you now think of this from a sampling perspective, so you, for example, you simulate the GLM for multiple voxels, and for all voxels you set the null hypothesis to be true. Then, of course, each time you get different values for the t statistic, but one of them will always be the largest one. And the question is now, what is the distribution of this? Or this would be the question for random field theory, but we already use this distribution now, namely in the following way. We select one critical value, which we call U alpha prime FWE. And what we do is, so we consider the probability at the locations where the null hypothesis holds for the maximum statistic to be larger or equal to U alpha prime, and we select this U, so this value of the maximum statistic, such that the probability for this to be larger than U alpha prime FW E is smaller than the significance level. If we do this, then, and this will be something that I will show with a little proof, then we control the family-wise error rate at the significance level. So what this means is we need to know distribution of max statistic, the maximum statistic. That's the first thing, otherwise we cannot do anything. this will be the big thing in random field theory. For now, we assume, okay, we just assume we know it. So we assume that we have already figured out all the random field theory stuff, and we know what the distribution of the maximum t-statistic is. If we know this distribution, then we can select some alpha prime FWE. So for example, 0.05. And then we can find a value, a critical value, u alpha prime, such that it's now a little bit less formal. It's just the same thing that I wrote there, such that the maximum, that the probability for the maximum to be larger than this u is smaller than alpha prime FWE. So what that means, if you think quite straightforwardly, so if this, for example, would be our maximum distribution, usually doesn't look quite like this, but just for example, so this would be the distribution of the maximum. Then we want to find some u here, so this would be our u alpha prime FWE, such that the probability for the maximum statistic to be larger than this is smaller or equal to our alpha prime. So we want to shift around the u such that the probability for the maximum statistic to be larger than this is smaller or equal to, for example, 0.05. Yeah, it's the same thing that you do with the t-statistics. So you find the critical value. So if you say you want, in a simple t-test, you want one simple t-test, you want to exert control of the type 1 error rate, you find a critical value, which is then something like 2.1 or something, depending on the degrees of freedom, such that the probability for the t-statistic to take on a value larger than this is smaller or equal to, for example, 0.05. And often then you actually have exact tests so that you can actually do it like this. Now, if you found such a value, and this is the last thing which is actually not in there, use this value, use alpha prime FWE for all tests. So common critical value u alpha prime FWE for all tests. Then the family-wise error rate is controlled at alpha prime FWE. So that means, for example, if you find that the critical value is something like 10, let's say, so this is 10, then if you reject the null hypothesis at all locations only if your t-statistic is larger than 10, if you again are going over voxels, then if you use this procedure, if you use this test, then you're guaranteed to control the family-wise error rate at this level. And why that is, this I want to show you now, but is this clear? So do you have a question about this procedure, how that works? No, good. So the question is, why does this control the family-wise error rate? Because that's not immediately clear. I'm just telling you that you should look at the maximum statistic. You should find a critical value so that the maximum statistics probability to take on a value larger than this critical value is smaller than the significance level, and then magically the family-wise error rate is controlled. It's not magically, so this is what I'm trying to show now, or will show now, that this procedure actually controls the family-wise error rate. So we assume that we have our test phi, which comprises all our phi I. So I'm just saying the obvious, and phi I takes on the value 0 if the test statistic I is smaller or equal to ui, and 1 if gamma I is larger than ui. And now we say ui, so the critical value for each individual test is set to this common critical value for all null hypotheses, and you can assume that not all of them hold or not. Now we define this thing to be, as we just said, namely as the critical value for the maximum statistic, or the value for the maximum statistic, to be smaller or equal to alpha prime FWE. Now the question is, how does this relate to the family-wise error rate? Now the family-wise error rate we've seen already is this. That's the probability over all two null hypotheses for the test to come out 1. So this is just the family-wise error rate. And this, of course, is the complementary probability to all tests where the null hypothesis holds to come out 0. Yeah? So this is 1 or more comes out 1. So the complementary, so the opposite event is that all of them come out 0. Yeah? And because these are complementary events, so mutually exclusive events, and the probability for all of them, for all, that's fine, sorry, maybe complete that. The probability for all of them to come out 0 is 1 minus the probability for one of them, 1 or more, to come out 1. Yeah, so this is this complementary statement. So again, the probability under the assumption of these null hypothesis for 1 or more to come out 1, the opposite of this is that all of them come out 0, and hence the probability is 1 minus this. Now, the probability that all of them come out 0 means that we're talking about the probability, again, it's a little bit annoying to always write this again, but whatever, under these null hypotheses, that all the test statistics are smaller than UFE alpha prime, where these I1, I2, and so on, they are the test statistics where the null hypothesis holds. And this is just because how we defined the test now. Yeah? The test is defined to come out 0 if, no, then I should make it strict here. to come out 0 if the test statistic is smaller than the critical value, and we defined the critical value to be the same for all tests. So all test statistics come out smaller than this critical value. Now, if all of these test statistics, so this test statistic, the first test statistic, the second statistic, and the last test statistic, if all of them are smaller than the critical value, then also the largest of these test statistics is smaller than this. Yeah? Because all of them are smaller than this. That means, so if, for example, 3.1, 4.2, and 5.6 are smaller than 6, then also the largest value of these three values, which was 5.6, is smaller than 6. So again, so if 3.1 smaller than 6, 4.2 smaller than 6, and 5.8 smaller than 6. So all of them are smaller than 6. This is what I'm saying right now. This means that also the largest of these values is smaller than 6. So this means that the maximum over these values like this. The maximum of these test statistics is smaller than U alpha prime FWER. And this is just writing it differently. I'm forgetting half of this here, but you see it in the script. It's a little annoying to write this again. This means that our maximum statistic is, which depends on the data, which I didn't write here. It always depends on the data, of course. The test statistic is smaller than U FWER alpha prime. Now, the maximum statistic to be smaller than this value here is, of course, the complementary probability to the maximum statistic to be larger than this value. Yeah, so here we have the probability that the maximum statistics is smaller than this, and we have 1 minus the probability that the maximum statistics is smaller than this critical value, this is the same as the probability that the maximum statistic is equal to or larger than, because either it's smaller than or it's equal to or larger than. And now we have already chosen that we want this probability to be smaller or equal to alpha, alpha prime FWE. This is how we chose our critical value here. And now we have seen that if we do this, then the family-wise error rate is actually smaller than this. Yeah. So the trick here is essentially that a little bit these complementary probabilities then go into the fact that all of the test statistics are smaller than the critical value, because the test is defined like this, and if all of the test statistics are smaller than the critical value, then also the maximum is smaller than the critical value, and this then proves that this test procedure here that I wrote down here, that this test procedure controls the family-wise error rate at a given level. So again, This doesn't yet show how the maximum is actually distributed, but if we know the maximum distribution, we can use the maximum distribution to define a test procedure, which is fairly simple. Namely, we look at the distribution of the maximum statistic, select the critical values such that the value that is the probability that is larger than this critical value is smaller than our control level, and then we use this critical value, for example 10, for all of the tests. If we do this, we have now shown that we then control the multiple testing family-wise error rate. And that's what's happening for family-wise error rate control in fMRI data analysis. The difference, I mean, we'll get to that, but the difference between voxel level is that and cluster level is that we look at the distribution. At voxel level, we look at the distribution of the maximum of the t-statistics over all voxels. At the cluster level, we look at the maximum of the cluster size over all identified clusters. So these are very different tests, but the way to control the family-wise error rate is the same. Namely, we look at the maximum statistic. So our big task then for the remainder of the term is to figure out how how a t-map, so for this kind of thing where we have t-values for all voxels, how the maximum statistic is distributed so that we have a probability distribution for the maximum statistic, which we then can use, like the t-distribution in one-sided t-test and undergraduate statistics, to identify critical values for all our tests. Yeah. Questions?
Is it possible at this stage to connect this with the concept of SR correction, for example, Bonferroni correction?
It's not that easy. No, it's Bonferroni is different. So for Bonferroni, that doesn't use the maximum statistics. So Bonferroni assumes some independence and then uses these inequalities. What are they called? I think they're called Boole inequalities to exert control there. So one can discuss Bonferroni, but this is not Bonferroni.
Okay, but this is equivalent in the sense that it also attempts to control for the fact that you are testing.
Yeah, so in this sense, yes. But it's definitely different from Bonferroni. So to introduce Bonferroni, in the past, sometimes I introduce Bonferroni. Currently, I don't have it in the notes. One needs a different framework that looks a little bit different, and then one can show that Bonferroni controls family-wise error rate. I think it also Bonferroni, right? So it also controls the family-wise error rate, but it does it differently based on an independence assumption. So the main difference between Bonferroni and this thing is that for Bonferroni, you need to assume that all the tests are independent, so that these test statistics are distributed independently, and here you don't need to assume that they are distributed independently. What you need here is the distribution of the maximum. So that's the fundamental difference. And for fMRI, of course, you don't want to use Bonferroni because the test statistics are not independently distributed because you have spatial correlations. So t-statistics from neighboring locations are more likely to co-vary, essentially in the error terms, than things that are further apart. And this is why in this maximum statistic, together with the assumption of spatial covariation, which will come in the random field part, is done. So Bonferroni is not appropriate for fMRI. Good. So then, if there are no further questions, I stop here. And then next time, we're finally going to start with random field theory. But the important thing is that you know why we actually discuss random field theory and why we discuss the distribution of the maximum statistic, which will be related to this Euler characteristic thing. And the reason is because looking at the distribution of the maximum statistics allows us to identify a critical value that we can use for all our tests. That then allows us to establish family-wise error rate control, which we want to do. Yeah? Good. Then see you next Monday.